Thanks for making it into this talk today. My name is Chris Beck. I'll be giving today's talk on Duoquest, a dual specification system for expressive SQL queries. Here's our agenda for today. I'll be beginning with the motivation behind our work. So first of all, relational databases and SQL are immensely popular. Relational databases are by far the most popular database model in use today. And secondly, SQL is known to be an essential developer skill. According to the Stack Overflow survey in 2017, is one of the most coveted languages in terms of developers. On the other hand, SQL can be really challenging, especially for non-programmers. So the following are a couple databases that are intended for use by non-programmers, actually, so an astronomer's database as well as an example business database. And we observe that the tutorial queries that are given here they actually have some complex semantics involved as well as syntax in terms of understanding the nature of joins, being able to issue subqueries on the right here. And it also requires that users have a knowledge of the details of the schema. So what does spec obj all mean on the left side exactly? As a result, the research literature has considered a bunch of different ways that we can tackle the problem of making SQL easier to digest for non-experts in particular. So to enable these non-experts to access relational databases, maybe there are three general approaches that people take. The first is to have these users learn SQL, and that's going to cost a little bit of time. The second is to hire technical middlemen as an organization who can do the dirty work for them. And this costs both time and money, actually. And the final one is to build more user-friendly tools. And this is the kind of approach that we'll actually be focusing on in this particular talk. Now, a lot of research has been done on possible alternatives to SQL. And so an example is the natural language interface, where the user just says what they want in natural language, and the system's job is to produce SQL queries. So consider this scenario where we're trying to find movies released before 1995 starring Tom Hanks on a movie database. On a natural language interface, the user might specify something as follows: find all Tom Hanks movies before 1995, and the system might return the following possible candidate queries. So movies with the substring Tom Hanks in their title, movies directed by Tom Hanks, movies with actor Tom Hanks. The user actually desires the third query, but the other two are not bad interpretations or incorrect interpretations necessarily. And that's where we see the pros and cons of this natural language interface approach, is that users can describe expressive queries, including aggregates, but that there's inherent ambiguity. And that's demonstrated in the state of the art, where the top one accuracy is only around 60% on a prominent benchmark, which is far from where we'd want it to be. Secondly, we have the PBE approach, where the user provides examples of output rows from the desired query. So going back to our Tom Hanks example, let's say that the user provided two examples of movies released before 1995, Forrest Gump and Big, in their corresponding years. The system might produce the following results. And all of these are valid because they satisfy the input specification. But there could be many, many more, especially if we permit more expressivity in the syntax of the resulting SQL queries. And so this is the pro and con of the PBE approach, in the sense that resulting queries are sound. They're guaranteed to satisfy the input constraints, which are a hard constraint. But on the other hand, more expressivity leads to a much larger set of queries ended up being displayed to the user. Our research question here is, given these two interfaces, is it possible for us to get the best of both worlds, to get the expressivity advantage of the NLI approach, but also to include the accuracy or the soundness of the PBE approach? To do that, we built a prototype system. I'll be showing a demo video, then going through some of the details.
Consider a database containing information about scholars and their publications. The user can issue a natural language query to find all authors from the University of Michigan and their total number of publications. For specific proper nouns and entities such as the University of Michigan, the system offers a list for autocomplete. In the next section, the user specifies some information about the output of the SQL query that they are looking for. The first column is for author name, so the user puts text for the column type and adds HV Jagadish as an example. The second column is for the number of publications, so the user puts number for the column type. The user cannot remember precisely how many publications Professor Jagadish has, but knows generally that it should be between 50 and 100, so they type this range into the box. The user then executes this specification. The results appear one by one in order of most to least confidence. The SQL appears complex to an untrained user, so as an eyeball test, they can preview the results of executing the query. The first query appears to be correct, and the user's task is now complete.
Now, some details about the way we approach that. Our goals essentially are to maximize accuracy and also to consider the efficiency of our algorithms. And as an overview, let's say that we go back to our Tom Hanks example and we provide both specifications now. The way we internally model the search process of finding SQL queries is to enumerate a syntax tree as follows. In this tree, each node is a partial query, and lower layers and lower nodes are more concrete versions of previous layers. So the bottom node here is a more fleshed out version of the upper one. And finally, when we get to the bottom of the tree, the leaf nodes are executable queries that we can run directly on the database. Now, this is a exponential space depending on the number of columns in the schema. And that begs two questions. So when we go through this process, how do we decide which branches to explore first? And secondly, how do we prune the search space? Now, the most naive approach is to just perform a breadth-first search to explore every branch and then end up and execute each leaf node to prune them. But instead of doing that, because it might take forever and we might not get the results that we want, our approach is to perform guided partial query enumeration. So guidance is provided by a deep learning syntax tree network, and that uses the natural language query information. And pruning is done by comparing partial queries against the PBE specification provided above. And I'll provide a little bit more detail about that pruning approach. Our goal of pruning is to minimize the number of verifications. What do I mean by verifications? Verifications are essentially running a database query to check if it satisfies the PBE specification that's given. That is to show that a candidate query includes the tuples given in the PBE specification. Now, this takes time. Every time you run a database query, it's going to take a lot of time. And so a naive approach is to go through and independently execute and verify each leaf node that's produced by our system. So at the bottom here, we have two very, very similar yet different queries. And we can go through, run each of them, check their result sets, iterate through them, see is Forrest Gump in there, is Big in there. But instead of doing that, we want to avoid this kind of redundancy and actually test partial queries. So these two leaf node queries actually have a common ancestor. And in that common ancestor partial query, the first column produces the genre result, the genre column. And in the genre column, there is no value for Gump or Big. They are not examples of movie genres. As a result, we can eliminate that partial query as well as any of its descendants, saving ourselves a ton of time by avoiding executing any of the leaf nodes produced as a descendant of that partial query. There's more details on kind of the algorithms in the paper, so I'd encourage you to read that. We'll talk a little bit about some of the experiments that we did. And so we performed user studies. We took 16 users with no prior schema knowledge. Some of them had some SQL experience. 6 of them had little to none. And we did 2 different studies, one comparing against a natural language interface, an NLI, and the other comparing a PBE against a PBE system. And we provided a fact bank where we gave each user 10 facts per task to be able to control for domain knowledge, because again, they're all coming in with no prior information, so we wanted to have an even playing field for our evaluation. When we compared with the natural language interface, these are the results that we got. The x-axis shows each independent task that we tested people on, and the y-axis shows the number of % of successful trials where users got the result that they were supposed to. On the aggregate, there's a 62.5% absolute increase in the total number of successful trials across all of these tasks. We also observed that the blue bars are higher for each individual task. And finally, on A3, A4, and B4, which are some of the more difficult tasks, there was 0% accuracy for natural language interface. Not a single user got any of those tasks correct. In our comparison with the PBE system, we did something similar. We had a different set of tasks here, and the reason was the PBE system has a more constrained workload. As we said earlier, the PBE systems have a limited ability to expand expressivity. So the natural language interface allows for a greater expressive set of queries. The PBE systems in the literature have a much more constrained set. So we built some easier queries to be able to provide to the PBE system. In that context, we see that we had comparable or higher accuracy over PBE on all tasks. We also did a simulation study not involving users. We tested on the SPIDER benchmark, which is a benchmark of many natural language to SQL pairs on many databases. It's split into a training, dev, and a test set. So what we did is, because this benchmark is a natural language benchmark and not a PBE benchmark, for the PBE specification, we executed the SQL, randomly selected 1 or 2 example rows as the input to the PBE. And we compared approaches where Duoquest takes in both specifications, and then the other systems take in their respective specifications. In terms of accuracy, we had 2 different metrics. So for our system and the NLI, we returned a ranked list of queries. And in that ranked list of queries, we measured the top 10 accuracy. For PBE, the system that we compared against returns a set of candidate filters, which are essentially selection predicates in the where clause. We considered it correct if the true filters were a subset of the actual filters that the system produced. So actually, this was a very generous metric. We're trying to give the greatest benefit of the doubt for the system. In that context, these were the results. We observe a greater than 27% absolute increase in top 10 accuracy using in the light blue bar over the gray bar, which is the NLI. We also observed that the PB could not even support 80% of the tasks. And so the dark blue bar here is really low. And it's the reason again is because of the limited set of expressivity that PB is able to provide. In conclusion, here are a few takeaways. The problem was that relational databases can be really hard to query, especially for non-experts and non-programmers. Our solution is a dual specification interface combining natural language interface and PBE, program by example. In our user study results, we observed a 62.5% absolute increase in accuracy over natural language interface and comparable performance to PBE systems on a more limited PBE supported workload. In our simulation study, we demonstrated a greater than 27% absolute increase in top 10 accuracy over the next best competitor. And that's all. Happy to take questions. Thanks for listening. And here is my email for any further questions.